Students of 641E, good evening, or maybe good morning or good afternoon, depending when you are listening to this. This video will hopefully help you to complete workbook 2 for this quarter. You should all have finished workbook 1 by now. If not, that needs to be completed and uploaded to the Google Classroom as soon as possible for me to mark. Now let's have a look at where we find the workbook 2, just to remind ourselves. I'm already on Google Drive on the shared folder, so you should be able to find that like always in physics. So let's go to, we're on level 4, quarter 3 now, and here it is, WB2, our second workbook for this quarter. So you can find this, all you need is the internet. You don't need any special this and that. Just click on that, and if you haven't already, which you should have done by now if you were following the distance learning instructions, you should have downloaded it and have it already stored somewhere on your laptop or your phone. I'm just going to do that now so that I can use it today in this lesson. So download. Now I'm using just the internet is all you need for doing these things. So we're going to avoid using things like Notability today, just in case you don't have the ability to have those kind of apps. Don't know why, but it wants me to download again. Okay, just save it somewhere on your device where you can remember where it is. I already have it saved, so I don't need to do this really. I'm just doing it to show you. Okay. So now it's saved onto my computer. I've taken it off the internet, off of Google Drive. I'm going to open it in PDF Escape. So I already have it up here. If you just type in PDF Escape, PDF escape.com. Important. This is something you can use. You don't have to use it, but I think it's okay. It works for me. It should work for you for editing the PDF. Click enter. I don't want to pay. I'm going to say free. This is all online, so all you need is the internet. Click on that one. I don't know if it works on the phone as well, so you might need a laptop or something, but you don't need to use this method. If you have Notability on an iPad, fine, use the usual way, do the normal way. This is just for, I know some students don't have Notability, they don't have an iPad, so this is a different option for you if you have a laptop, which a lot of people have, and it's the same for me. I don't have Notability, so I'm using this. It's a free online software, so you don't even need to download anything. Now you want to go to upload, because otherwise we won't have anything to edit. Choose file. Now you can just drop it straight in if you want, or you can find it in your files, but I'm just gonna, oh, it says failed. Oh, yeah, it failed. I'm just gonna drop it straight in because I've got it here. Hopefully that works. Okay, so now it's in. Is this, yeah, this is the correct workbook. So just check, obviously it matches up. with the one you've just seen on Google Drive. Yeah, level 4, quarter 3, workbook 2, same thing. So that matches up with what we want. Here we go, PDF Escape. Now this software, online software, lets us edit whatever we want. So if I want to write in now my student number A000 WB2, fine, that works. I can change the font up here if I want to make it bigger. That's a bit small. You want to see student name, whoever it is. You get the idea. You can just enter it in. Let's make that a little bit bigger again. Teacher, that's me obviously. WB641. You know how to do all this. Sign this here, so you can go to a freehand tool and do that. Whatever it is, your signature. And a lot of us, we forget to put the date. I always try to. It's no good. There's a whiteout tool here, which is quite cool as well. So you can just put a box around something and it vanishes. Let's do that in text. Whatever the date is. So this should be done at the start. You know all of this anyway. I'm just going through it all, reminding us the basics. Alright, let's get into the physics now. These always useful to know the Arabic term for some key words. We have that in physics at the top of the workbook, each workbook. They're useful, but we'll go through them as we go through the workbook. So I won't talk about them all right now. Just know that they're there. If there is a word, if you're reading and you don't understand, go back to the top of the workbook and see if it's there. Alright, here we go then. So this is the first 2 lessons. There's 4 lessons we'll cover today in this video. Let's look at lesson 13 and lesson 14 to start with together. Now some of this I'll fill in with you, some of it I won't, because you should be able to do it with my instruction. Alright then, so let's have a look. The first thing we need to understand is there are 2 types of material behavior that we can imagine. The first type is elastic. Now, what do I mean by material behavior to start with? A material is anything like a certain, so this is made of plastic, this is some of this pen here, this bit is made of metal. This material is paper, so all the materials are different. You know this. Material behavior, what a material does, right? What behavior is, what are you doing? So a material behavior is what a material does. Now materials, they can either, when you stretch them, go back to their original shape, like an elastic band. Or sometimes materials, if you stretch them, they will not go back to their original shape. So if I pull this too hard, I actually break it and it doesn't go back to its original shape again. So part of the material has it's behaved differently now. Something different has happened to it. A good example of when things go back to their original shape is elastic bands. Now here is my, these are actually my laces from my running shoes. I like to put my running shoes on fast. I do things called triathlons, where I have to get off the cycling and into the running very quickly, so I don't waste time. I don't want to waste time putting my laces on, so I have my elastic laces for triathlon, and yeah, they look, I can stretch them and they go back to the original shape. This type of behavior is called elastic. Easy to remember because of this is an elastic band, right? The name of the elastic band is the same as its behavior, usually, unless I stretch it too much and it breaks. Now, a good example of not elastic would be, let's take this paper for example. Now, just like the elastic band, it can be elastic or plastic. So if I just move it a little bit, okay, it's going back to it. I'm changing the shape, but it goes back to the normal shape again. Now, if I move it in a different way, okay, it's not going to go back to its original shape anymore. So this is a different kind of behavior, and we can call this behavior plastic behavior. That sounds strange because it's the same as the name of material for, say, this mouse is made of plastic, but the behavior is either elastic, goes back to the normal shape, or plastic does not go back to the normal shape again. It's changed shape now forever, just like this now has changed shape forever. And it depends on the material. It also depends on how much force I use. I use a small amount of force, it's fine, it goes back again. I use too much and I'll break it. It will not go back to the usual shape. So this should help you answer the first two questions here on the pop quiz, fill in the blanks. Whether a material is plastic or elastic behavior. Alright, I will do the first bit here. If a material goes back to its original shape, so this one, is this elastic or plastic? Have a think. That's elastic. I don't imagine you will be filling this in whilst you watch the video, but it's one way you could do it. If you have a phone to watch the video maybe, and a laptop with your workbook up ready to edit, that's an option. So if you think that's a good way to do it, if you want to do it at the same time, then just press pause now and see if you can set up so that you have the phone and the laptop working together. One to complete the workbook on whatever notability, and one to watch my video. Now, of course, it might not be a laptop, could be a tablet or whatever you have. So if it's elastic, what happens? Now, we haven't talked about this word yet, particles. That's just what is made, what this is made of. Everything, all mass is made of particles, all stuff is made of particles. So in this case, the particles, now it's going to be do or do not go back to their original positions. Well, is this going back again after I let go of the force? You can decide. Now, the material does not go back to its original shape. It's changed shape forever. We call it the other thing. It's not the elastic one, it's the... Which one is it? You have 4 choices here, so that should be, you should be able to fill this in now. Maybe pause the video whilst you fill it in, if you need some time. Otherwise, I'm just going to carry on. If you're not filling it in as we go, you can just watch the whole video through. Now, there's also a nice video here you could watch. You can just click the link and watch that. It will be talking about the same things really as I've just discussed, but it might also go into the next thing, Hooke's law. I'm not going to click on that. You can pause my video and watch that in your own time. That's up to you. There's no point me videoing a video. So the next thing we need to learn about, we call it Hooke's law. Hooke's law is an equation, basically. Now this law is saying that if we apply a force to something, it will change its shape by a certain amount. Some materials, they will follow Hooke's law. A spring is a good example. Not many things are perfectly following Hooke's law, but if we have a spring, usually we can use it. We can use this equation to find out how much the spring stretches or goes the opposite of stretching. We call to compress. So to make smaller, I can compress something by giving it less length. Now springs, sometimes you stretch them, sometimes you compress them. A good example of a compression spring, can you think of any where we squash the spring, make the spring shorter? In a car would be a good example, so you think about it. Let me just, if you want, at any time you can pause the video and just Google some keyword compression here, making the spring shorter. If I just put compression suspension, this is part of your car, so you all hopefully know about this idea of suspension to keep the car stable when you're driving, to absorb some of the energy when you go over the bumps. And you'll have these springs in above your wheels. So this equation is used when you design your cars. I say you, when somebody designs your cars, to make sure you get the right amount of compression. Get nice and smooth ride. Alright then, so let's have a look at the next part. We'll talk about this equation more. I think this whole workbook is really focused on this. So we can increase the force. We'll change the shape more, right? If I pull a little bit, I get a little bit of change of shape. If I pull with more force, I will change the shape even more. I will get more stretching. We call that extension. That's why there's an X there, X for extension, or actually X means displacement in physics. In this case it means extension. Talk about K later, but this relationship is basically saying the more force we put in, the more it changes shape. Here's a nice example. We're in a stretching spring now, so it's not a compression spring. If I put a mass on the end, it will stretch as the weight force pulls it down. That's the force of the spring. Now that will be equal to the negative of K. Now K is something called a spring constant. K is the spring constant. It says it here. It's a number for the spring that tells you how easy it is to stretch. Now different springs have different stretchiness, right? It's going to be very hard to stretch or compress a spring in your car. They're very strong springs, right? You're going to need the Superman to squash that spring. But in your pen, for example, some of you might have a small spring in your pen. Let me see if I can find one. Okay, I found one of my pens. Now I'm going to try and take this apart. So inside my pen here, got a very small spring. There we go. Now this has a very small K value because it only takes a very small force to change the shape of the spring. I can do it with my fingers. So the K value is maybe 1 for this spring. Of course, I don't know, might be 10, might be, but it's a small number compared to, let's imagine now, go back to the car example. Where's my car example? These really, really powerful springs. There's a nice picture. See the spring in there? Spring on your car wheel. This spring, I'm not going to be able to just do this. Oh, look. I'll be the strongest. I'll have the strongest fingers in the universe if I can do this. So the K value for this, maybe it's, I don't know, 3,000 or something. A big number. Very big K value. So this is what K is, and it's a fixed number. We call fixed numbers in physics a constant, and it's a fixed number for each different spring. Material property of the spring. Okay. All right, let's go back to my PDF. So, okay, this is, if I put, it's got an example here. If I put a bigger mass on, it's gonna stretch more. So I've got twice the force. Here I've doubled the mass. So I've doubled the force. So I've got double the stretching. Here it only stretched by X. Here it stretches by 2x, twice the amount of extension. So that makes sense because F is proportional to X. Remember that keyword, proportional? Because K is a constant, K will not change. It's just a number, a fixed number. If we increase one, we increase the other. Let's scroll down. They've just rearranged the equation there to simplify it. I got rid of the negative. Now, most of the time we don't really, we don't care about this negative. It's not that useful to us because we're only going to look at the magnitude. Magnitude doesn't care about direction. And most examples, the direction is obvious. If I put a mass on this, the spring's not going to go up, is it? It will be pulled down. So we can forget about the minus most of the time when we look at magnitude, and we can draw the equation again without the minus. They even rearranged it there. Look, you can see it's the same equation. They just moved the x. It's multiplying on this side, so if we move it to the other side, it becomes divide f over x, f taxim x. Alright, so let's move to the first task. I think there's lots of similar questions here. Now you're good at doing this. There's nothing too tricky about this stuff. I'll do the first one as an example, and then you guys can get stuck in. So let's see what we have here. Remember, x is the extension. It's how much the spring changes length. So a spring is suspended from a bar. You can just imagine it just like this. Suspended just means to hang. I'm hanging something. There's a 6 Newton force. So immediately I'm just going to write, I know something. I know F equals kx. And I know F, so let's just write F equals 6. Yeah, newtons, that's the unit for force, so I'm happy with that. It's not the answer, and it's the right units, so I don't really care about writing the units right now. It's not important. What else does it tell us? The length changes from 0.04 to 0.13, so the length is increasing. The spring is stretching as the spring is loaded. Now there's actually, doesn't actually tell us x. There's two different distances, x the extension. Now there's an equation for x, which we haven't covered yet. The extension It's actually delta x, the change in distance is equal to the it's going to be the change in length. So we've got the final length. This is if something is getting longer, minus the start length. It's the big length minus the small length. If you want to find a change in length in something, you have to find the difference in the lengths, right? So what's the difference between 0.04 and 0.13 if something is getting longer? Okay, that's easy enough. So now we can find x, because I know that, and that's the first question, find the extension. Find the extension. Extension means x, right? So just a note, x is extension. I want you to get confused there. And that's how much the spring stretches. So simple maths, what are we going to do? The final length, it's going from this to this. So which one is the final length? I would think this one or this one. Okay, you've probably got one of those numbers in your head. We're going to go with this one is the final length because it got longer, right? You're stretching it. And before I stretched it, it was 0.04. So that's the start length. And then we can find x, which will be the extension, which is the question. So let's just put that in the calculator. You can finish that. It's easy, just do the maths. We'll do this as a full example, so I'll just put that in now. What do we got? 0.09. Some of you won't need the calculator for that. You can do it in your head. M, don't forget the units. The units, it's a length, right? How far did it go? Did it stretch? And the units for distance are always meters. We don't have to convert anything there because we're in meters and meters. Just finding a change in length. Great, next question then. Let's move down. It's the same questions. Find the spring constant. So the first thing I'm going to write is k equals question mark. That's what I want to find. Spring constant, k for k. I know it's not the same letter, but it's the same sound. So that's how you can remember that one. And the spring constant, all right, well, I need to find k. I've got an equation for it here. It's the force divided by the extension. So let's have a look. We've got the force. Oh, we just found the extension, so let's do it. Force is, oh hang on, k is force divided by extension. So that's going to be the same as saying 6 divided by, what was it, 0.09. What I found for x, right? What did we get? 66.6 recurring. You don't need to write 6 100 times. We'll do this to 3 significant figures. A lot of you will write, well, there's 3 numbers, that will do. But remember, whatever the fourth number is, if it's bigger than 5, we should make the third number the next number up. Is 6 bigger than 5? Yes or no? Well, yes it is. So my third number should go up 1. So I should make that 7. Now we don't need this number, we don't write it because we're writing only to 3 numbers. We just use it to find out what the other number will be. So I haven't worked out how to delete text easily yet. But there's a whiteout tool here. Let's get rid of that. Okay, is that the final answer? hopefully. Some of us said no. Because, well, think about it. There's no units here. What did I do? I did force, which is newtons, divided by extension, which is meters. So newtons dash meters. Yeah, that's it. There's no special unit for spring constant, just like speed is meters per second, distance over time. So we can just write N dash M, newtons per meter. Remember, N is capital always, because it's named after a person, Isaac Newton. Maybe that's the reason, I don't know actually. There we go, final answer. Usually I ask you to put a box around the answer. I can't find an easy way to do that. So we'll just leave it. Oh, here we go. Here's my answer. Not sure if that works. Don't worry about the box. You've got the two things that you're gonna need to do. You're going to need for all these questions now. That equation, k is f over x, or the extension, finding extension, the big number minus the small number of length in the question, usually. You might have to rearrange that. There is a triangle formula for it. So if you're used to using the triangle method, they haven't shown it here, so I'll just write it. The triangle method will have a f on the top and we'll have a k and an x on the bottom. So that's what the triangle method would look like. Try and draw some freehand with this. Not sure how this will go. Here's my triangle. Remember that's a times in the middle there. It's going to be confusing because you've got x there already. Okay, I can't draw. This is true. Just gonna put x. So spring constant times extension would equal the force, because if we cover up the f, then that's what we find, right? So I need the force. So what am I gonna do? Spring constant times extension. I need the extension, so cover it up. What am I left with? Force, taksim, k, right? So k is the spring constant. Remember, I can just cover the thing I want, and I can always use this if we are not good at rearranging the equation. I always say it's better to learn this way though, if you can, because some equations are not simple like this. All right. With question 2, it's okay. It gives you extension. Gives you extension here, stretched, so we don't have to calculate extension this time. It just tells you x equals well, it's not 5 because this is centimeters, so we have to do it divide by 100 to find it. 5 over 100 to get to meters, because the units for length are always meters, or extension. Tells me the spring constant k is here. You guys can do the rest. You've got k and x. Use the triangle method to find the force. Question 3. Again, we're in centimeters. So let's just convert to standard units. What do we divide by? We just did this. 6 divided by 100 will tell us x, extension, right? It's a distance. Tells me the stretch, how much stretch. this time we've got a mass. Now to make mass the force of weight, the weight force, which will be the same as the spring force in a simple example, we just times by gravity. Now gravity is the same number always on Earth, on the surface of Earth. So we just say, okay, this is getting complicated because I don't even have kilograms. I don't have kilograms here, so I'm going to say that 200 need to divide by 1,000. That will give me the mass. Now I need to do the mass times the gravity. Don't like how those x's are the same as the... You get the idea. If I do mass times gravity, I will find the force. Okay? So I take that number, I've got in kilograms now, because I want grams to kilograms, and then I times by gravity on Earth, which is always 9.8. We'll assume we're on Earth. It doesn't say that, but let's use 9.8. Every planet has different gravitational field strength, remember? So we'll just do that number times that number, and we find F. And then we've got F and X again. Well, now we have F and X. It asked us to find the spring constant. Oh, look, F divided by X. You can finish that question yourself. But this step here, where we go through the mass and then do the mass times the gravity, this is something they like to add that extra step in. So really, when you're finding, whatever you're finding, you have to convert that mass to kilograms and then times by G. Right, question 4 is basically same idea. You have to use mass times gravity here. It's in grams again, G, not kg. So again, divide 1,000. This time, the same spring. It says if you use the spring from problem 3, so the K value will be equal to whatever answer you got from question 3. Because it's asking you to find the spring constant. Well, if it's the same spring, it will have the same spring constant. And again, you can do mg, which will equal to F. Don't forget to convert the grams. Then you have F and K. How far will it stretch? So you're finding the stretch. You just need to go back to your triangle, F over K, right? All right, F over K. Need X, the extension, the stretch. Extension means stretch, same thing. So cover F over K, done. Forget units are meters. I just want to go X equals question mark. All right, not doing any more of these. This is all the same stuff. This time you have to find the mass. That's a little bit harder, you have to go backwards. But if you know K, tells you spring constant. Yeah, and you know X, says it stretches 8 centimeters. And you can find F. I know it doesn't tell you to find F, but you need to find F so that you can find M. Because many will do this unless I put the template up. F equals mg, right? The weight force is the mass times the gravity. So rearranging that for m, I want to find the mass. I'll just do whatever the force is that I found using the triangle formula up above. So I have F from this. You can write in the K and the X. It's here, look. Convert this, divide 100 centimeters. Divide G, rearranging for M. So that's your final answer. Once you have the F, you put it into here and you divide by 9.8, remember. G equals 9.8. So what's your final answer? Will be m equals something, and your mass is always kg, right? That's why here we need to convert because it's in g. I want to divide by 1,000. Always use the standard units if you can, just as a rule. Alright, you have to go at that one yourself. There's nothing new in that one. Okay, we got stretch. Extensions, we've got k and x. Find the force. Alright, so that's our first lesson complete. Took a bit longer than I thought. Let's go straight into the second 2 lessons of this week. Obviously write something in here. Tell me what you learned all about Hooke's law, that equation. That was the focus, right? Maybe you learned about this idea of the spring constant for different springs. Alright, let's check this out. So what are we trying to do in this second half of the video? Define Hooke's law. So what is Hooke's law? We've kind of done that already. And apply it to situations. So it looks like after the introduction we gave earlier in the video, now we're just going to use it even more. And look at this pop quiz. Well, it's exactly the same kind of question as we had. We're just using our f equals kx knowledge. Well, there's k, look, spring constant, constant for k. So I know k is 10, I know x is 0.3. What force does the spring exert on the block? Alright, well, strange picture, but it shows what's happening. The mass is moving away, it's stretching the spring. So I know k, which one is it, 10 or 0.3? 10, right? Spring constant, k. And what's this then? It's pulled 0.3 meters. Is that the force? No, force is measured in newtons. So let's put that as my extension. X for extension. How far it's stretched. 0.3. Yeah, it's in the right units. Check the units. Always look, you're not centimeters there, you're not millimeters, you're in meters. That's what you want. We're just going to find the force to hold it motionless. If we want it to just be held, you need to apply the same force. You need to balance the forces. So whatever the spring force is must be the same as the force you hold it with. So we can just find the spring force and say, well, that's the holding force. It must be balanced, right? If it's not moving. Motionless. No motion. Not moving. That's that word. Okay, so go back to your triangle and solve that one. It's nice and easy. Finding f. Where's my triangle? Finding f. So cover f. What do I need to do? Okay, verb x. Super. Okay, looks like we're doing a new equation today. We could find how much the spring stretches, or the force of the spring, or the spring constant. There's one more thing that we need to be able to find, and that's how much energy we can store in a spring. Springs are very good at doing that, and in fact that's their very purpose, is to store energy in the spring. If I compress this spring and then I let go, so I've stored some energy in it, I let go. I'm going to try and do this. Come on. Okay, I've lost that spring forever. It probably happened too fast for you to see it, but it's now somewhere on my lounge floor. Gone forever. I'm sure I'll step on it later. But the point is, well, where did it get all that motion from? From the energy it's stored in itself. Springs store energy, and we can call this elastic potential energy. We can calculate it using this equation if we have the extension and if we have the spring constant. So looks like this is what we're going to practice using today, this other equation. And let's get straight into it. I don't think there's much more. We can check out this first question. Now this is, like I said, a bit harder. We can't use the triangle method so easily now. We cannot use it. So, all right, let's see what we've got. We've got the same question as we've just done, so that's a bit strange. Never mind. I'm not going to do that because we've done it already. There's a part C now. I see what they've done. All right, well, okay, find the extension. It's the change in the length. So if it gives you two lengths, usually we just do the big one minus the little one. We did that before, didn't we? We just said 0.09. Now, if they only give you one length, they probably gave you x already, so we don't have to do anything. But sometimes they're cheeky and they tell you the length changes, so we have to be clever and say, well, I know it's the x is actually changing length, so there's my extension. Done this already as well. We said that it was going to use my equation f equals kx. So if I rearrange it, f over x equals k, which is 6 over 0.09. I've already done this as my example with you, but we need to do these first two steps to solve the next problem. Now part C, the last step now, it tells us to find the elastic energy in the spring. Now if it was not nice, it would just say find this. And you say, well, I can't, I don't have K or X. But you could find K or X using the numbers. So it's one of those sort of 3-step problems, and they've made it A, B, and C to make it simpler for you. So find the energy. Well, I'll look at my equation. E, energy, that's easy to remember. E for easy for energy is just half kx squared. I know K. There it is. I just found the spring constant. And I know X. I just found it. I have to square it. Don't forget, if the 2 is small, we have to do it squared on the calculator. So let's do that now. So I'm going to do a half, which is 0.5. Let's just write the whole thing down. E equals half K. Not going to do the times. Kx squared. There's a squared function here. Let's go for freehand. Fine. So E is going to be 0.5 times by whatever K was, 66.7. Now we'll get an inaccuracy in our answer because we already rounded that. So if you save the number 66.6 recurring in your calculator, you can get a better answer. So I should really maybe more accurate here. Put a load of 6's in there. And x squared, 0.09. Well, squared is just timesing the number twice, right? So I can just write times 0.09. That's the same as if I say 0.09 squared, it's the same as saying 0.09 multiplied verb. I don't know how to say that word in Arabic. 0.09 times 0.09. So let's do that in our calculators. This will be my example. 0.5 66.666 So we've got here, it must be one of those tiny springs like in the pen, because it only stores 0.269, right? So 269. I want 3 significant figures, so I just pick the first 3. I'm going to chop it off, but I'm going to see if this number is bigger than 5. It is. So instead of writing a 6 here, I'm going to write a 7. Because it's closer to 7, right? 0.269 it's close to 0.27. And why did I write J? That's the unit for energy. The unit for energy is joules. Joule. I think that was a French engineer or physicist, I should say, probably, who named that unit after his own name. So J for joule. Could write joules. We don't usually, we save ink. Just write J. Alright, then let's have a look. The next one, find the force. So now we have to rearrange that equation. Well, this equation doesn't even have force in, so we're just using the same equation as we used before to find the force now. So it's F equals kx, right? I'll let you do that. You don't need me. Just remember to divide by 100 for your centimeters to meters. Yeah. Then you've got k and x. You need to try and find f. Oops. Let's get rid of that. So yeah, so you can find the force on the spring and use F equals kx, your old equation from the last lesson, and just find the force on the spring, F. Right, we know K. The spring kick a constant, K, 0.5. You know x as well. I'll let you calculate x, but you need use k and x to find f. You just go back, all the way back, and just remind yourself of this equation to find x. Cover the x, f over k, right? Easy. Find the elastic energy stored. Well, how much energy am I storing? Of course, the energy I stored is depending on two things, these two things. How much I stretch it. If I stretch this more, I'm going to store more energy. If I stretch it less energy. So that's why that's part of the equation, the extension. And K, well, if I have a very strong spring, a very high stiffness, we call it stiffness of spring, then it will store more energy. So K effects as well. I'll let you do B because we've done an example there already of that, half kx squared. You've got the K there, you've got the X. Just need to put the numbers in. Put the numbers in from here. Half kx squared. Give that a go. Don't forget your units for energy, joules. Joules. Right, that's everything for this week in terms of the workbook. Just write something in there about, yeah, I can calculate elastic energy. Just give you an example. Oh, I'm doing this in capitals. Using an equation. What did you enjoy? Who knows? Maybe you enjoy sitting at home, having a cup of tea, a cup of carrot. That's it. Right, if you have any questions about anything from this week, you need to just message me on the WhatsApp group. Now, if you want to message me privately, not on the group, that's maybe better, because you can't see the group. There's messages coming every 5 seconds, so find my name and number in the group and just message me privately, because otherwise I'm not checking the group every 5 seconds. Good luck, guys, and stay safe, and I will see you when all this settles down, hopefully sooner rather than later. But all right, good night. Ma salama. Oh, don't forget to obviously save your work. So now let's actually go through that. Let's go through that. Yeah, I knew I forgot something. So I've written on all of this, right? But it's not saved anywhere, so you're going to lose everything unless you download it from the internet. So on the left here, you can see the green button, save and download PDF, and click on that. So let's check this out. That's downloaded. Just open it. So la la la. And all my stuff is written in. Whatever I wrote, it's saved, right? But it's not really saved anywhere I know, so I just download it again on the top right here. Now this is just how it looks on Windows. I don't know about other things. And of course, if you have Notability, you know how to save it anyway. This is just for students with other laptops and things. Save it with your A number, whatever it is. Find somewhere, find some folder, who knows where, and just save it. I'll just save it to the desktop now, and because I remember where it is, and I can go to my desktop and it should be there somewhere. Here it is. I just click on that and it's back. Okay, don't upload to Google. Do not upload to Google Classroom. That's the last thing I will say. If you do that before, you know that already, right? You need to only upload to Google Classroom only if the assessment is done. And you do that at the end of week 6. All right, so that's week 4, 641. Good luck and good night.